This is Chapter 8, the Joviate Planet Systems. Our goals for learning are what are Jovian planets made of and what is the weather like on the Jovian planets. This is a comparison of the 4 Jovian planets to Earth, which you see in the upper left, Jupiter, Saturn, Uranus, and Neptune in the order of increasing distance from the Sun, which is the first detail you see underneath each of the planets. The masses are shown, as well as the overall densities of the planets and the compositions of those planets, which are fairly similar. So what's the planet's compositions? Well, Jupiter and Saturn are mostly hydrogen and helium gas. Uranus and Neptune have a combination of water, methane, and ammonia. There's also some hydrogen, helium, and rock material making up the interiors. So there's a slight difference between the 2 innermost Jovian and the 2 outermost Jovian planets. Beyond the frost line, apparently small planetesimals, small chunks of rock, could accumulate ice. And then the hydrogen compounds are apparently more abundant than the rock and metal. So Jovian planets got bigger and acquired hydrogen and helium atmospheres. So again, the inner 2 got most of the hydrogen and helium during formation. The Jovian cores are very similar. They have a mass of about 10 Earths, but they differ in the amount of hydrogen and helium gas accumulated. So the question is, why did that amount differ? Well, there was a timing difference. The planets that form earliest captures the most hydrogen and helium gas, and that capture stops after the first solar wind blows the leftover gas away. And then there's location. The planet that forms in a denser part of the nebula forms its core first. So timing and location made a difference in how the planets formed. Here's a graph that shows the density differences. Uranus and Neptune are definitely denser than Saturn because they have less hydrogen and helium. But it doesn't explain how it doesn't work for Jupiter. So we need a different way of explaining that. Adding mass to a Jovian planet compresses the underlying gas layers. So this analogy of pillows is very good. The more pillows you stack up, the higher the pressure will be at the bottom, making the density at the bottom higher. So let's look at the sizes of the Jovian planets. Now, the greater compression is why Jupiter isn't much larger than Saturn, even though it's 3 times more massive. So that was due to compression. Jovian planets with even more mass can be smaller than Jupiter, and of course they are. So what are the interiors of the Jovian planets like? Well, they have no solid surface, and the layers are under very high pressure and temperatures. The cores themselves are about 10 times the mass of the Earth, made mostly of hydrogen compounds, metals, and rock. But the layers are different for the different planets, and the question is, why? Well, this is inside Jupiter, and as you can see, it consists of course, the cloud tops, hydrogen in different forms, and then, of course, the core. So the high pressure inside Jupiter causes the different phases of hydrogen to change with depth, and the hydrogen acts like a metal at great depths because its electrons are allowed to move freely. So this is all due to very, very high pressures. The core is thought to be made of rock, metals, and hydrogen compounds, and the core seems to be about the same size as Earth, but about 10 times more massive. So we obviously have a much larger planet with a very, very thick layer of hydrogen in different forms, and then a solid rock core. So this is a nice picture showing the different Jovian interiors. It suggests that they have similar composition, but because of obviously smaller size, the lower pressures inside Uranus and Neptune means they have no metallic hydrogen. Again, that would mean that the electrons are flowing freely under the extreme pressure. Jupiter has a very, very strong magnetic field. Very strong. And so different things can happen with Jupiter compared to the other planets. For example, the photograph on the right shows what appears to be something like Aurora Borealis on Earth. These are auroras due to the interruption of the sun's or the solar wind by Jupiter's magnetic field. So gases escaping Io, for example, feed the donut-shaped Io Taurus, Io being a moon of Jupiter. What's the weather like on Jovian planets? Well, as we've seen with lots of different pictures of Jupiter, there appears to be something called a great red spot. And that great red spot is apparently very similar to a storm or a circulating pattern of gases in the atmosphere of Jupiter. Of course, because of rotation, there is a twirling or a spinning or rotation of the pressure center. Whether it's a high pressure center or a low pressure center, they tend to rotate depending on the hemisphere of the disturbance. So, Jupiter's atmosphere. Hydrogen compounds are found in the clouds. Different cloud layers correspond to freezing points of different hydrogen compounds, and other Jovian planets could have similar cloud layers. So, based on the science of hydrogen and the freezing point or the boiling point of those substances, it's possible to estimate what those cloud layers are like. Jupiter's colors. There's a definite difference in the colors of some of the clouds. Ammonium sulfide reflects a reddish-brown color, and then ammonia, just plain ammonia, is the highest cloud layer, coldest. It's reflecting kind of a whitish color. Saturn's colors are similar but deeper in and farther from the sun, so they're a little more subdued, as you can see here. But definite bands of color. That's the interesting part, where apparently rotation is causing different compounds or elements to group into these different colored bands. Methane gas on Neptune and Uranus absorbs red light but transmits blue light, so we get kind of a bluish color emanating from these planets. The blue light reflects off the methane and makes the planets look blue. Jupiter's great red spot, as I mentioned before, is what we think a permanent storm within the atmosphere of Jupiter. It's a storm twice as wide as Earth, and it's been there as long as we've been able to observe Jupiter with a telescope, 300 years. So all the Jovian planets have strong winds and storms. Seems kind of obvious since the planets are so big. They have a higher rotation rate, and because there is so much gas, those gases can rotate at a faster rate, and that's of course what wind is. So, what are the Jovian planets made of? Well, Jupiter and Saturn are mostly hydrogen and helium. Uranus and Neptune are mostly hydrogen compounds. They have layered interiors with very high pressures and cores made of rock, metals, and hydrogen compounds. And especially Jupiter and Saturn are under very high pressure close to the core, so they have in their interiors metallic hydrogen. What's the weather like on Jovian planets? Well, multiple cloud layers determine the colors of the Jovian planets, and they all have very strong storms and winds. Now let's look at section 8.2, satellites of ice and rock. What kinds of moons orbit the Jovian planets? Why are Jupiter's Galilean moons geologically active? And what geological activity do we see on Titan and other moons? And why are Jovian planet moons more geologically active than small, rocky planets? Here's a picture of some of the Jovian moons: Io, Europa, Ganymede, and Callisto. And as you can see, even by these photographs, they're very different in size, color, texture, so we'll look at these in more detail. Small moons are less than 300 kilometers in diameter. no geologic activity, as we've talked about with terrestrial planets. The smaller the object, the faster the moon or planet cooled, so that object would be dead geologically. There are medium-sized moons which have some or have had some geological activity, and there are large moons that are still experiencing geological activity. So you look at the differences in sizes of these moons, and there is quite a bit of difference depending on the planet they orbit. There's, with the larger moons, enough self-gravity to be spherical. Some have substantial amounts of ice. They formed in orbit around the Jovian planets, and most have circular orbits in the same direction as the planet rotation. So it's generally a counterclockwise rule for revolution or orbiting and rotation. The small moons are much more numerous than the medium and large size moons, and because they are so small, they didn't have enough gravitational pull to bring everything together into a spherical shape. So many of them are oddball or potato shaped, as you can see. So why are Jupiter's Galilean moons geologically active? That's the question, as you can see on page 222. Io is the most volcanically active body in the solar system. But why? As you can see from these photographs taken by spacecraft that have flown by, there's some things going on the surface that are very interesting to scientists. Things that are changing even as spacecraft flew by. They were able to see volcanoes erupting on Io, for example. Volcanic eruptions continue to change Io's surface. So again, as spacecraft were able to visit this moon, the moon being so active, we were able to see volcanoes erupting. Io is squished and stretched as it orbits Jupiter. So Jupiter being a much larger planet, having a much larger mass than any of the other planets, it also has a much larger tidal pull on anything that orbits it. So that pull also distorts or changes the shape, actually changes the shape of the orbit of Io. So not only do we get this more elliptical orbit, but we also get tidal heating, as explained in the diagram, where the forces of Jupiter, the gravitational forces of Jupiter, actually stretch and pull at the moon. But why is its orbit so elliptical? Well, there's something called orbital resonance. Io's orbit is elliptical because of the orbital resonance Io shares with Europa and Ganymede. As you can see, those other two moons, which are also very large, have different sized orbits compared to Io, and every 7 days these three moons line up. So that would be like a spring tide for our moon and Earth, where there's a much larger pull of a much larger tidal pull because these three objects are lined up. The tugs add up over time, making all three orbits elliptical, as it turns out. Here's Europa. Looks like a big glass marble, but we're wondering if there's water there. There's definite evidence of tidal stresses that have cracked the surface of Europa, giving it kind of a, sort of a cracked marble effect, as you can see here. Europa's interior is also warmed by tidal heating, just like with Io, although, as you can see in the middle diagram picture, there appears to be maybe some ice on the surface, but then maybe liquid water down below. Ganymede is the largest moon in our solar system. It has clear evidence of geological activity, but we're wondering if tidal heating plus the heat from radioactive decay is keeping it geologically active. As you can see in the little inset there, and this is also on page 225 of your book, There's a difference in certain parts of the moon surface where there's a heavily cratered area versus young terrain with few craters. So apparently this portion in the upper right has experienced some movement, maybe due to some kind of plate tectonic activity. Here's Callisto, a classic cratered ice ball. Appears to be no tidal heating, no orbital resonance, but it has a magnetic field. And of course the question is why, or what has formed, or what has allowed this magnetic field to form. So there's a very, very heavily cratered moon. So what geological activity do we see on Titan and other moons? Well, Titan is the only moon in the solar system that has a very thick atmosphere. Compared to Earth, there's a definite blue haze around it. It consists of nitrogen with some argon, methane, and ethane. So these are nitrogen-heavy gases, except for argon. And of course, nitrogen is something that almost 80% of our atmosphere is made of. Here's photographs from something called the Huygens probe that provided a first look at Titan's surface in 2005. It had liquid methane and rocks made of ice. So as you can see from the surface photographs, it appears to be kind of a desert-like environment in some areas there. So although it has an icy surface, it may be something that would be usable at some point in the future. Here are Titan's lakes. They've revealed some dark, smooth regions that may be lakes of liquid methane. Again, methane is a combination of nitrogen and hydrogen. So apparently this moon has been able to capture and allow to cool to a point where methane could actually exist in a liquid form. Now here's some of the medium moons of Saturn. Mimas, Enceladus, Tethys, Dione, Rhea, and Iapetus. Almost all of them show evidence of past volcanism or plate tectonics. So apparently these moons, although medium in size, have experienced some geological activity. There's ongoing activity on Enceladus, as you can see in the inset there. Fountains of ice particles and water vapor from the surface of Enceladus indicate that geologic activity is ongoing. So it's kind of indicating, like you see in the same picture on page 228, that there's something happening within the interior that's causing ice and water vapor to actually flow out of the surface. There must be something heating the underside of these areas that are causing these eruptions. So we have kind of like ice volcanoes. Medium moons of Uranus have varying amounts of geological activity too. This moon, called Miranda, has some very large tectonic features and a few craters. So it might have experienced some tidal heating, which caused the surface to rupture, crack, possibly move. So the same pictures on page 229 of your book. Here's Neptune's moon, Triton. It's similar to Pluto, but it's larger. And again, there's evidence of past geological activity. Certainly what appears to be impact basins, or the remains of impact craters, but lava of some type was flowing out and filling up those impact craters. There appears to be what looks like wind streaks, so possibly there's an atmosphere there, or was an atmosphere, and even frost deposits, similar to what we might find on Mars today. So why are Jovian planet moons more geologically active than small rocky planets? Well, the rock melts at higher temperatures, and only large rocky planets have enough heat for activity. Ice melts at lower temperatures, and there's tidal heating that can melt the internal ice, driving the activity. So we basically have a difference in composition here. Rocky planets versus icy moons. So what kinds of moons orbit the Jovian planets? Well, there are moons of many sizes, and the level of geologic activity depends on that size. So you should remember the general classifications: large, medium, and small moons, and what sort of activity you can predict. And then why are Jupiter's Galilean moons so geologically active? Well, mostly because of tidal heating, like Io, leading to volcanoes and ice geology on other moons. So the gravitational pull of the planet that the moon is orbiting is apparently something that is causing this tidal heating. What geologic activity do we see on Titan and other moons? Well, Titan's the only moon with a thick atmosphere. Many other icy moons show signs of geologic activity. And why are Jovian planet moons more geologically active than small rocky planets? Well, because ice melts and deforms at lower temperatures, enabling tidal heating to drive the activity. The last section has to do with the planetary rings that all Jovian planets have. So what are Saturn's rings look like, and why do the Jovian planets have rings? Here's a sequence of pictures that shows Saturn, not only in an earthbound telescopic view, but then something from the Cassini spacecraft that took a much closer up view of those rings. And finally, an artist's conception of what the particles in the ring system might look like if we were able to analyze them. This is all at the top of page 231. Apparently, Saturn's rings are made of numerous tiny individual particles that orbit Saturn's equator, and the ring system is very thin. This is an Earth-based telescope view of Saturn, making the rings look very large, concentric sheets, but this dark gap within the rings is called the Cassini division. This image, taken from Cassini, reveals many individual rings separated by those narrow gaps. So this is a much higher resolution view that we had compared to an earthbound view. And again, the artist's conception of those particles in the ring system. The particles clump together because of gravity, but small random changes in velocity cause collisions that break them up again. Then there are moons, called gap moons, that kind of create ripples or gaps within the ring system. And as you can see in the inset, we've discovered the actual existence of these moons and sort of the path that they plow out in the ring system. So why do the Jovian planets have rings? This is a beautiful set of photographs on page 232 showing the ring system of all of the Jovian planets. Well, we do know that all the Jovian planets have ring systems, and others have ring particles that are smaller and darker than Saturn's. Saturn's is the most obvious, but as you can see by the photographs, all of them have some sort of a ring system. Well, the idea is that they form from dust created impacts on the moons orbiting the planets. How do we know this? Well, the rings aren't left over from planet formation because the particles are too small to have survived this long. So there must be a continuous replacement of those tiny particles, and the most likely source is impacts within the Jovian moons. So if we could actually fly through or stop very quickly inside one of these ring systems, chances are the particles we would find would be the same consistency, the same type of particle, same type of rock as what we would find in one of the moons around that planet. Jovian planets all have rings because they possess many small moons very close in. And impacts on these moons are random. At least that's what we think as far as ring formation. So, Saturn's rings are made up of individual ice particles. The rings are extremely thin with many gaps. And why do the Jovian planets have rings? Well, although the other Jovian planets have rings that are much smaller, darker, less numerous particles, we think the ring particles are probably debris from their inner moons.